Hello everyone, welcome to this video about Terraform. First, we will look at some basic concepts and then move on to a small project to see Terraform in action. The first question to address for why you are here: what is Terraform? Terraform is an open source infrastructure as code tool developed by HashiCorp used for infrastructure provisioning or management of cloud provider or services. Infrastructure provisioning generally involves setting up, building, and configuring the infrastructure and making it available to the users and the system. It supports multiple cloud providers which you can provision infrastructure for, like Amazon Web Services, commonly known as AWS, Google Cloud Platform, Microsoft Azure, Oracle Cloud, among many others. The idea of Terraform is to provide a consistent CLI workflow to provision infrastructure consistently with the same configuration in environment. Next, we will talk about what the infrastructure for Terraform looks like. At the heart of Terraform is HCL, not the chemistry one, mind you, but the HashiCorp configuration language, which is what you write the code in for infrastructure provisioning, which we will look at in the consequent slides. If you take a look at the diagram on the right, you're the practitioner here, which will write the HCL code to provision the infrastructure. Now, when you write code, you make use of the plugins from the public module registry written by the Terraform's team itself or the community for different providers, which in turn makes API calls internally to the provider to do what the used module describes. Now, Terraform provides command line interface to interact with the Terraform core and to provision your infrastructure. So once you write your code, you use a few simple commands as shown here, which executes your code and make API calls defined in the modules of the provider you used to deploy your infrastructure. Finally, the provider's platform receives the API calls, after which it will deploy your resources as per your requirement and configuration. Now we will look at the HashiCorp configuration language, the HCL. As stated earlier, Terraform achieves the infrastructure as code part using the declarative language called HashiCorp configuration language, which allows you to perform infrastructure provisioning. It being declarative means that you just write some code dictating what it needs to do, but not how it will do it, like in some other programming languages like Python, because Terraform itself figures out what order it needs to follow. In HCL, you declare a bunch of blocks where each block is dictated by the type, the label, and the properties within it. So in this example from our project, we have two resource blocks. Let's look at the first block, which creates an S3 bucket on your AWS account. You see, in a single block, we have a bunch of properties that configures the block, like this bucket property, which sets the name of the S3 bucket upon creation. Every block in HCL is configured similar to this example right here. You might have questions about how do we know which properties to write and which resource label creates what kind of resource. Do not worry, later in this project, I'll address that concern of yours. You can also write comments like in this resource block with a hash or pound sign, so it is helpful for other developers or maybe yourself when you come back to it after some time. Now we will look at how Terraform manages all of that. The way how Terraform keeps track of what is happening or what has happened in the past is through the state files. Generally, when you apply a plan or apply changes, Terraform generates a terraform.tf state file locally, just like shown in the picture on the right. You can choose to store the state file remotely and use that if you're working within a team. Now, the state of Terraform is affected by the commands you run for Terraform's core on the command line interface. In the next slide, we will look at what 4 basic commands for Terraform are and what each of it does. The first is init, which stands for initialization. When you run this command, it checks plugins or provider used and downloads them to execute the code. Then we have plan, which looks at the desired configuration, the current resource state on the provider's end, and compares them. This might update the state and generate a plan which you can review to see what is to be added, changed, or removed on the provider's end to meet your configurational need. Once you have reviewed the plan as to what the Terraform will do, using the apply command will execute the plan on the provider's end, meaning it would make the API calls and deploy the services and resources. Now to go back to where you started, meaning if you want to undo the process Terraform performed, you can use this destroy command to do so. It will roll back all the changes made on the provider's end by the Terraform. So now you see there's a cycle between plan and apply. What this basically means is that once you apply and have deployed your changes, you might realize that, oh, I might need more resources, or maybe you do not need the resource you added before. In that case, you make changes again, run the plan command, review your changes, and apply them, as simple as that. You only move to the destroy command in case you don't want your infrastructure anymore. And oh, don't worry, we'll run these commands in our project ahead and see the process in action. This section is divided into 4 concepts and then an overview of the files themselves. The one we will look at first is the concept of root and child modules. Terraform has a concept called a module directory. Whenever you create files within a directory, that is a single module. Every module might have some files like main.tf, variables.tf, and outputs.tf, or maybe even more. So in this concept, the root folder directory is the root module where the Terraform files reside in. Inside the root files where your TF files are, you might have more folder directories. Since they are contained within the root module, you can call them child modules. In Terraform, the root modules are the primary module, which make use of the child modules, kind of like a library, similar in concept to other programming languages. We'll look at this concept ahead. The idea behind the concept of reconciliation is that internally you can think of that Terraform looks at all files as one. Meaning, if you were to write code in a single file, instead of dividing into files like main, variables, and outputs, that would work as well, with the exception of the .tf vars file, which we will look at later. What logical division means is that we divide code into different files, where each file name depicts the purpose of the file and the code it might have within it. So for example, a outputs file would contain output blocks, and the variables file might just contain variable blocks. Due to convention in Terraform, the minimum amount of files you divide the code into per module for any project should be main, variables, and outputs, all with a .tf extension. Another concept that we'll see next is thinking of modules as functions, meaning you give them some input, they do something, and once done, they return something as an output. So let's move on to the input variables. The input variables are the blocks declared with the variable type. Like input parameters for a function, they act as the input for a module. Really, it's a similar concept here. The root module references the child module using a module type block. In properties of that block, we use a property called source, in which we specify the directory of the child module we intend to use, so Terraform could go and use the code in there. The rest of the properties of a module block in the root module are dependent on what variable blocks the child module use. In the project part, we'll look in more detail on how you can reference child modules in the root module and how it makes use of that. Similarly, just like a function has an output, and relating to what we discussed before, you can specify in modules what you would like to expose to the parent module, So whatever you return can be used by the parent module. This is achieved by using an output type block. A use case of it is, let's say you are creating an EC2 instance for AWS within the child module, and you need an elastic IP assigned to it as well. For this purpose, you can specify the EC2 instance's ID and output of the child module. So when the parent creates an elastic IP resource, it can access that instance ID of EC2 to give to the elastic IP resource block. Now you might be wondering, hey, we know where the output of child module goes, but what about the root module? And that is a good question. The root module's output is handled by the Terraform core. The output can be given to the terminal. One use case of it would be to output some URL of a resource from the root module and use that output URL given in terminal for a script that builds an app. Finally, let's look at what files we have in total and what each of it contains. The main.tf file primarily contains resource and module blocks, hence the name main. The variables file contains the variable type blocks, which are the inputs as discussed before. The outputs file contains the output type blocks. Finally, we have another file at root module with a .tf-vars extension. This file is used to store secret API keys and other similar files that you do not want exposed within the code or to the version control system. Generally, you add this file to the ignored list within a version control system. Now that we know about some basic concepts and file structure, let's move on to a scenario for using Terraform. Now for our tutorial, we will look at a scenario on what we will be provisioning and deploying to AWS. Let's say you have a website on React that you have to deploy on an S3 instance of AWS, a Node.js backend server that would be running on an EC2 instance, and finally, a relational database like PostgreSQL on an RDS instance. What you will do is define a provider and write the infrastructure as code. You will then apply the basic commands we talked about that run on Terraform core, which will then make API calls to the cloud provider, and finally deploy our instances. Easy, right? So without further ado, let's get to it. Before we move on to the practical, it is necessary to install Terraform on your system. Now you can install Terraform either manually or through the command line interface as shown here. There's a nice documentation on this HashiCorp webpage with this installation guide. I will follow the command line interface installation because it is easier and automated. Since I'm using Macintosh, I will be following this section and install Terraform. If you have other operating system, they have the instruction for them as well. Once installed, you can verify if Terraform installed correctly by using this command, which will show you the version of Terraform. Now, before we move on to the tutorial for setting up infrastructure for your application, make sure you have Terraform installed and an AWS account set up. Now you can use any search engine you like. I use Google and search for AWS console login and click this link here. You'll now see a AWS console management login screen here. Once you're on the login screen, sign in or set up your AWS account. There are a few steps you have to go through, first of which is creating the actual user and assigning an administrator policy to it. Terraform requires administrator access to your AWS account, so it can manage all of the resources through it without being limited by different access limitations. So once you have your AWS account set up and signed in, you will see this screen right here. It's called AWS Management Console for managing everything AWS. From here, you can go up and search for IAM like this and select it. Here, IAM stands for Identity and Access Management, which allows you to control access to your AWS services and resources. From this dashboard, select Users from the navigation bar on the left. So once you're on the users in IAM, you can click Add Users on the top right corner here. On here, you will see a username field. For our tutorial, I'll use the name Terraform Tutorial. You can use any name you like for this user. For the access type, you will select Programmatic Access since you will be using APIs and Terraform to manage instead of AWS Management Console. Here, you will assign the administrator permissions policy to the user as mentioned earlier by clicking Attach Existing Policies. AWS provides some permissions policy for general use cases such as the administrator access policy right here, which is perfect for us. Therefore, select it and hit Next. We do not need to add any tags for the user, therefore click Next. Here you can review your information and finally click Create User. If the user has been created successfully, you will see this message right here. Now there are three properties of the user: the username, the access key ID, and the secret access key. Make sure you hit Show and save the secret access key somewhere for Terraform access because it is not available from AWS account after this, unless you want to create a new user all over again. Once you have done that, you will return to your users page and see your user created. Now that we have set up our user for the project and saved the keys, it's time for us to move on to the project. Expanding upon the scenario in the slides, here we'll actually create some files, have some overview on the code we add, and finally move our code to the application we are looking to deploy. Right now we are in an empty directory I created. Next, what I like to do first is load up any text editor of choice. I like to use Visual Studio Code, you can use any you like, and open up this empty directory in it. I'll just move the directory window on the left and the editor on the right and zoom in a little bit so you can see better. Anyway, keeping what we had learned in mind, we'll create our main file first to add resources we need and create more files that we need as we go. For now, I'll add the code and show you the file creation and the process. Later, we'll focus on just the code. Since we need Terraform to connect to the service provider, we need to set up a provider type block first so it can do exactly that. Once we have the AWS provider block, we need a virtual network setup for our resources. For that, you add an AWS VPC resource type block with the proper CIDR block defined. Next, we'll need to create subnet for our VPC to put our resource into. The RDS instance has a requirement of creating two subnet availability blocks. Therefore, we add both of them. Now, since we need to reference this VPC and the subnets in our other block definitions, we need to define a locals block so we can reference them between the code. Now let's add more networking blocks we need, such as creating a subnet group for our RDS instance, adding security group blocks to allow connections to database from our EC2 instance, and HTTP connections to the EC2 instance from the S3 instance, and finally a SSH connection to the network for, let's say, connecting to our EC2 instance. Next, we'll add our final two resources that are an internet gateway for our virtual network and an elastic IP for our EC2 instance. Once you're done with that, you'll see that the elastic IP requires an instance ID of our EC2 instance, which is our server. So we have to create the server module and use the instance ID of the resource which our server module creates. But before that, let's look at what variables we need in the main file and add those first. So you create a variables.tf file and add the variables block in it that are present in the main file. So now we'll create the server module by first creating a server folder in the root directory. Now to add the resources of the server, we create a main.tf file and open it. Now we add the AWS instance label with a resource type block for an easy to instance in AWS. Once we have that resource defined, we can go back and see that the Elastic IP resource required the instance ID of this resource. So we go ahead and create an outputs file, which will give the parent module the access to the instance ID of this resource. Now the main file in the root module can reference that. After that, we'll look at the input variables that the EC2 instance needs and create a variables file to add those variables block into it. Now that we have created our module, we need to use the server module in our main file on the root directory. So once we add that, we need another variable called Amazon Machine Image ID, short for AMI ID, that we need to use. So we define its variable block in the root module's variables file as well. Now for the variables at root, we do not have a default value. So we can treat those as secrets and create a terraform.tf vars file, which will house all those values. Now we will add definitions for those variables, which Terraform can use as the values for those undefined variables. Now you see our server depends upon the RDS instance, therefore we create that as well. We follow the similar strategy as before and create a Postgres module folder for a database and add a main file. Similarly, we add the resources in it and check the input variable it needs. Once we figure out what input variables the module needs, we create a variables.tf file and add all of them in it. Finally, once we are done with creating the module and the variables, we can move on to the root module's main file and use the Postgres child module with the name taskdb. Here you will see we need two more variables on root module, which are actually secrets called database username and database password. So we add their variable block in root module's variables file and define the value of them in terraform.tf vars file. Now one more thing. Here we add the address of the database as the output if needed, so we can use that for connecting our server to the database through it. Since we are on the subject of adding outputs, we need to add the output of the public IP of the EC2 instance so we can later use it for our front-end applications environment or to SSH into it. Therefore, we create a outputs file in root module and add the module's public IP. But you see here, the output block here accesses the public IP through the module block. So we need to add that to the server module's output as well. Now we have done that, the root module can access the value and output it to the command line interface. Now we clean up the tabs that we do not need. And finally, we create our final module for the front-end application. Just like the two modules earlier, we follow a similar approach, that is, create a main file, add the resource block we need, check what variables you need for it, add them to the variables file, and finally, use the module in the main file on the root directory. In this case, you see we only have one input variable, so we add that to the variables file. And since we do not need any outputs from the S3 instance, we'll leave the outputs file empty or just delete it if you want. Now we are done with the creation of the app resource module. Therefore, we now add it in the root module. With this, our coding part is now complete. Now that we have the Terraform project ready, we add that to our project application. You see, we have a Terraform project here that we just created. After that, we'll get our application and copy this Terraform folder into it. Now that we have our file set up, we'll open this project directory, talk about the code itself, and see Terraform in action. Now you see we have all the files here that we have seen earlier in the lecture. I have my React app in this app folder, my Node.js app in the server folder, which also connects to the database and initializes it. First, we will look at the main file because that's where we configure the provider and use our other created modules. So in HCL, the first thing we define is the type of the block, followed by an optional label and an identifier depending upon the type of the block. In this case, you can see the type of the block is provider, therefore we can call this the provider label. Since we require AWS resources for our project, I have supplied AWS here. For the provider block, you see there are a bunch of properties like profile, region, access key, and secret key. Note that we had saved the access key and the secret key before. Now we supply it to the provider block here so that the Terraform can access our AWS account to manage and create our resources. You'll see how we have supplied the keys here. But first, let's move on to the other block. You see, this is a different type of block. The type of this block is locals. Now you see the locals type block does not require any labels or identifier ahead of it, so we do not provide it and start adding properties to the block. The local properties act as a variable like in other programming languages so that we do not have to type all of this over and over again. An example of accessing the local variables is seen here. Next, you see there's a resource type block followed by a resource label and an identifier. A way of thinking it is that you might have many resource blocks with the same resource name. So to identify each one of them, we provide an identifier name to it. Similarly, it has a bunch of properties that configures the resource. Now, as we had touched earlier, the providers we used are present in the Terraform public registry. Conveniently, Terraform has a website which lists all of those plugins and modules. This is actually the site created by the Terraform team where you will find all the information about plugins and their module. Since we need to use AWS, we can find its information on this AWS page. On the top right hand corner, you see there's a Use Provider button, which you can click and see the similar things that we had defined in our code. From here, you can click Documentation and come up to a page which lists all of the modules within the provider. You can see on the left, we have a list which contains different resource modules for AWS. Now let's find the same VPC resource we saw in the code. Now there are different resources like EC2 and EKS for AWS. Since we need VPC module, we look for VPC here. Around here, we can see there's a VPC module. We can click that and browse the resources within it. Since we need to create the actual VPC, we can click that, which will come up with a resource page with some examples and the different attributes or arguments that you can use with the resource. So in the code, we had defined a CIDR block, which has a short description ahead of it. Now that we have seen how we define each resource in the main file, we will now look at the variables file in our project. As we had discussed earlier, variable files are inputs to the module. This variable file currently is at the root module, so defines the variables for the main file that we had seen earlier. Now, you see we have the access key and the secret key defined here, along with other variables that we might need in our module. So if we go back to the main.tf file, we will see we are using the var.access key and the secret key here. The syntax to use it is to use var followed by a dot and the name of the variable that you had declared in the variables file. I had mentioned in the earlier part of the lecture that there's a tfvars file that is used to declare secrets such as the access key and the secret key along with the username and the password of the database. So we can browse that and see that we have access key, secret key, and the other fields defined here. I've added the other fields for the sake of the tutorial. You do not have to add additional fields in this file. So the resources are declared similarly in the other child modules of the project. We can look at each of them and see how they are declared. You can see we have a AWS instance resource followed by the identifier app server for our server module. Similar is the case with the main.tf in PostgreSQL file and the app module file. As we had discussed earlier, Terraform considers the files at the root module as one and executes the code. Therefore, we have to use the modules that we had created somewhere in the root module. Here I have declared the modules at the bottom of the main.tf file of the root module. Here I have 3 modules used that I had created within the Terraform project. The module block is declared by using a module type followed by a module identifier. For the database child module, I have used the name task_db. To tell Terraform which resource we are referring to, we use this source property and assign a directory to it, which contains the Terraform files. The other properties are dependent upon the input variables of the child module. We have a username, password, and other properties for the child module. We can verify this by going to the child module directory and to the variables.tf folder. As you can see, we have username, password, and other variables declared here. Finally, the output files. We use the output files in the root module to get the output through the CLI on the terminal to perform some actions with it. In child modules, we use the outputs to expose some properties that the root module can access from the child. As I stated earlier, this process is like a function. You give some input to the child module from the parent module, and then the child module gives an output in return to the parent module. We can look at the example of this in the main.tf file, where I'm using the server's instance ID for our Elastic IP resource. We can verify that the instance ID is declared in the server module by going to the server directory and into the outputs file. You can see there is indeed instance ID declared here, along with a bunch of other properties that the root module can utilize. We have declared total 15 resources for our project. 5 resources are declared in the child modules and the other 10 within the root module. As we had discussed earlier, we have to use the Terraform init command, so Terraform can download the dependencies it needs for the provider to execute our code. You can use an external terminal or the terminal that opens up within the text editor. Since it is easier to use this, I'm going to utilize that. Now, once you run the Terraform init command, it will download the resources. Once you have successfully downloaded, it will show that Terraform has been successfully initialized. So now you will run the Terraform plan to see what Terraform will do on the provider's end. Next, we will run the Terraform plan command so that Terraform can compare the AWS platform resources that it might have created in the past and the ones in the configuration file. Since we did not use the command before, it would only show that we have to add the resources but not any to be changed or destroyed. You can see right here that it is verified we have 15 resources to add, 0 to change, and 0 to destroy. And it will show what outputs the root modules have set for our project. You can see above that it has listed all the modules and resources that we had declared in the application. So once you have reviewed that, you can run the Terraform apply command. However, before that, let's verify that the information shown is correct by going to our AWS Management Console and see that we have no resources created or running beforehand. So once you're on the same AWS Management Console, you can go up to the search bar and look for EC2 instance, since we need that for our server application. As you can see, we have no instances running or elastic IPs created for our AWS account. We can look for an S3 instance now, since we need that for our front-end application. You can also see that we have no S3 buckets created before running our Terraform command. Finally, we can also look at our RDS service and see that we have no instances created for it as well. So once you have verified that the information is correct, you can go ahead and apply Terraform apply. Note that the RDS instance for SQL will take up to 5 minutes for AWS to deploy. Terraform, before applying, will show the plan again and wants to verify, which we will verify by typing yes. Now, Terraform will start deploying our infrastructure to the provider's end. Finally, the resources are deployed successfully. You can see we have 15 added, 0 changed, and 0 destroyed. Next, we can verify that the resources are indeed deployed successfully by going to the AWS Management Console. Once we are on the Management Console, and since we are already on the RDS page, we can refresh it and see that our RDS instance is indeed deployed. You can see our PostgreSQL RDS instance has been deployed successfully. Next, we will go to our S3 service and see that our bucket has been created successfully. Similarly, we can check our EC2 instance by going to EC2 service and see that we have an instance running and an elastic IP created. We can also check our VPC, which contains the subnets for all our resources. You can see we have 2 subnets in this region. The one is the default one created by the Amazon, and the one we have created for the tutorial. Now that our resources are deployed successfully, we might have to scale our infrastructure by adding or removing resources. Let's say we need another subnet resource in our infrastructure. We can add it by adding a new subnet block and name it a subnet 3, assign a new CIDR block. So once you have done that, you'll have a new resource to be added by Terraform. Let's say you have to change another resource. We can do so and check that Terraform detects the changes and resource to be added. Since we have already downloaded the dependencies for our provider, we do not need to run Terraform init again. Therefore, when we run Terraform plan, we show the changes and resource to be added. As you can see here, we have a new resource to be added and a resource to be changed. It will show you the resource that is to be updated and the resource to be added right here. So once you are satisfied with the plan, you can go ahead, use Terraform apply to see your changes. Finally, we might need to roll back all the process Terraform had performed, and also, since I'm using free tier and do not want to be charged, for that, you can just perform your Terraform destroy. And once you run the Terraform destroy command, it will ask you to confirm the operation. After reviewing the state of Terraform. So once you have reviewed your plan to destroy all 15 resources, you can type yes and wait for it to undo all the process. Now you can see all of our 15 resources are destroyed. You can verify this similarly by going to your AWS Management Console and see that they have indeed been destroyed. Since we are on our VPC resource, we can just refresh it and see that our VPC no longer exists. Similarly, we can go to our other resources and see that they do not exist anymore. So that was a quick overview on what Terraform is, the components involved, and how it works. I hope you all learned something about Terraform from this video. The code used in this video will be given in the description box down below. If this video helped you, make sure to like and subscribe, and also comment down below if you'd like to see more videos like this. Thank you.